Hi everyone, my name is Kamil, I work in Allegro Group. As you can see, the subject of my presentation is a little bit general, and because we don't have much time, I'm going to speak only about one, but in my opinion, the most important aspect of Swift runtime, that is method dispatching. It's not going to be easy soft presentation. I rather show you a lot of binary meat. So how many of you have dealt with assembly language? Okay. For most of people, assembly language may look like this, but I'm sure after this presentation you will see on this screen methods, classes, and the woman in red who just walked by. Okay, let's take a look under the hood. First, let's talk about Objective-C method dispatching to compare it with Swift method dispatching. So, Objective-C compiler takes every method invocation and translates it to invocation of Objective-C message send function, passing an object, method selector, and all the parameters. So basically, message send function takes care of methods dispatching in Objective-C. Maybe we should look to the internal pseudocode. It looks more or less like this. First, it takes a class from past instance. It executes in constant time. Then it tries to use internal class cache to find implementation of the method. This is as fast as searching for something in hashmap. So relatively fast. But in case of cache miss, message send has to take a little bit longer path. So it uses this method, get method implementation. And that method is terribly slow. It searches through all selectors, through all methods in class, then in superclass, and down to the root of the hierarchy. And at the end, it cleans stack frame after itself and jumps directly into the method implementation. So that how does it look. And before talking about Swift method dispatching, we have to get familiar with two different things. First of them is name mangling. It's essential for the linker because Swift allows you to define, for example, two classes with the same name but in different modules. Moreover, it allows you to method overloading, so you could define two methods with the same names in the same class. And linker would have problem with that. So compiler needs to encode those names and make them unique. Let's take a look at some example methods. First two of them are the methods speak in AI program class. And they are overloaded. First one takes a string argument, second integer argument. And the third method, it's a method from class from different module, from Sentinels. And you see that class methods don't clash. So let's have a look how those method names look after applying mangling algorithm. It's not pretty human readable. You don't have to think about this in everyday development, but we have to be aware of that in the next slides, in the next part of our presentation. So the string here is reflected here, and we can see the difference in this part. Here the integer is preserved here. Same stands for the module. You can see that sentinels is reflected here. And that's why those names don't clash. They can coexist. Okay, if you would like to demangle method names for yourself, you can use this handy command. It's shipped with Xcode. And if you would like to read more about method mangling, then it's no better place to read about this than mycache blog. Anyone it takes square? No?
Yes.
Okay. So the next thing we talk about is Swift compilation. How does it work? So it consists of several phases. The first phase is when Swift frontend takes Swift and translates it to the high-level platform agnostic Swift intermediate language, SIL in shortcut. In the second phase, SIL optimizer takes SIL, optimizes it, and generates low-level, still platform agnostic intermediate representation. And you can watch output of every of those phases using emit_sil parameter passing to Swift cell and looking at IR code passing emit IR parameter. In the third phase, there is some IR optimization, and on the last phase, code generator takes IR and gives us assembly. So if you would like to see assembly before it's taken by the assembler to output binary, you can use large S parameter. Again, you don't have to use it in everyday development, but we will use it in current presentation. If you would like to read more about Swift compilation, there is a nice blog post on this site. Okay, let's get to the point. Virtual method table is a mechanism used in not only by Swift but C++ to support dynamic runtime method binding. So let's have a look how does it look in Swift. This is an example code that we will use. There is an agent class. Agent knows basic Kung Fu moves, so punch, kick, and jump. And there is a subclass, Smith. And let's assume that Smith can jump a little bit different. There is a method override. And he can also laugh. He does this all the time in the matrix move. So let's have a look how does vtable looks in the SIL code, in the Swift intermediate language. It looks like that. This is basically a dictionary mapping method names to the functions. Those functions method names are mangled, so let's demangle them. And now we can see that agent method punch defined in agent, it maps to its original implementation. The same for the method kick, it maps to original implementation, but method jump, originally declared in agent, it maps to different implementation, to implementation from the Smith class. And at the end, we can see that there is a method laugh, and it's declared in Smith and maps to original implementation in Swift. So we have to step a little into assembly. So let's skip IR representation. And what we have here, this is basically array of pointers to functions. We can see dictionary here. there are only pointers to the functions. And what happened to our dictionary? Let's just leave it for a while and take a look at our test method. This is a function that tests agent Kung Fu abilities. So it takes an agent object and invokes its jump, punch, and kick methods. We're not going to show how seal and IR looks in this example. We'll directly jump into assembly, but it looks very easy. I had to remove all the arc management code, but it all executes in constant type. And I left that's what's more important. So in the first line, we have global symbol definition. In the second line, you can see RDI. RDI is a register that on Intel architecture holds value of the first argument to the function. Our test Kung Fu function has only one argument, that was the agent, so RDI basically holds a pointer to this instance. And you may know or know there was some post about this, that instance in Objective-C, it's basically a structure, and the very first thing in that structure, it is a pointer to meta class. So in the first line, there is the reference of that pointer, and in the RCX, it just puts pointer to the meta class to this RCX register. And the next three things is just invocation of some functions, some computed addresses of functions. Let's change it a little bit. Let's generate pseudocode. And that's basically what I've just told. There is the reference of agent pointer. We get pointer to the meta class. And then those three invocations. They look like this. They add an offset of 88 bytes to meta class, cast it to the function pointer, and just call it. So now take a look back to this assembly vtable that we had before. And now something strange. It's probably an implementation detail. We don't have to worry about this. This meta class pointer points to the third element of the metadata. Don't worry about this. That doesn't matter. What matters is that when we add 88 bytes, on the left side I added some addresses for help. They are hexadecimal. And if we add 88 bytes decimal to this metadata pointer, then we get reference to the jump implementation. So this basically executes like that. We have pointer to the implementation of jump function, and we just invoke it. So if we think about this, the dictionary structure of the vtable didn't disappear. It just morphed somehow. In the seal representation, we have dictionary where keys were strings. And here, keys for the dictionary are offset in the metadata. So every method call is transformed to this operation of on pointers. Okay, it's time to wrap up. So what have we learned? Swift methods dispatching uses vtables. Okay, and because of that, method dispatching in Swift is much faster and simpler than in Objective-C. And that wasn't everything that I wanted to say today. If you declare a method as final, Swift doesn't use this vtable to dispatch it. It just directly call the memory, the place in memory where this implementation is. And where you pass optimization flag to the Swift compiler, it likes to inline all of those functions, and it works even faster. So in a few days, I'm going to write a blog post about this and much more. And you can follow my Twitter. I will announce it. So thank you.